All right, let's get started. Welcome everyone to the second day of the HDX and Codes workshop. So morning session, we have two talks in the first session. David Lin is the first speaker who will tell us about a lot of things: Sheaf codes, cup product, quantum LDPC codes, transversal gates, and so on. David, if you're there, let's start.
Yes. Okay. Yeah, thanks. Okay, so today I want to share with you some ideas that brings together sheaves, cup products, and quantum LDPC codes with transversal non-Clifford gates. Yeah, so this is not about a specific paper per se, but rather like a collection of ideas that I've gathered across several of these projects. So in short, my goal would be to give you a high-level picture of like how to make sense of codes in higher dimensions. Okay. So two important works that exemplifies this connection between high-dimensional expanders and codes are the recent breakthroughs on locally testable codes and these quantum LDPC codes. So in particular, both of these codes utilize some kind of two-dimensional structures. Okay, but why? Like, why should we go to like higher dimensions? So usually a code is described simply by a parity check matrix. Yeah, but in both of these cases, there are some additional structures. So for these locally testable codes, their parity checks, it's ideally that they have some sort of linear dependence. So there are actually some redundant parity checks. And for quantum LDPC codes, as we'll see later on, their X and Z parity check, they actually has to be orthogonal. So there is some extra structure that's required. But the point is that these structures can be succinctly captured using these chain complexes. So you might have learned about this in Pavel's lecture. And in fact, these chain complexes can be naturally induced from these two-dimensional structures. And so that was one of the reasons that to construct these locally testable codes or these quantum LDPC codes, you're naturally required to go to at least two dimensions. But more recently, we have found reasons to go like move even beyond 2D to explore even higher dimensional structures. And so one of the motivation is to construct these quantum locally testable codes. So now you not only have X check and Z check, but also relations between them. Yeah, so that naturally brings you to 4 dimensions. And indeed, using these kind of idea, you can actually get quantum locally testable codes with nearly optimal parameters. And in fact, like Pavel later tells us about one of the key ingredients to obtain this result. But there are some other motivations. Another one is to construct codes with these kind of a computational ability. So in particular, like the AND gate. So the AND gate is really like a multiplication for Boolean values. And so in the quantum case, turns out these multiplications become this notion of cup product. And to obtain them, you actually have to go to 3D. And that's another reason why you want to go to even higher dimensions. And so in this paper with Louis, we have used this kind of idea to construct quantum codes with these multiplication abilities. But it's not optimal yet, but it's one of the best code with such property at this moment. And so actually, eventually we might want to go to even higher dimensions to get quantum locally testable code with these multiplication features. Yeah, so here I'm just illustrating some reasons that why like studying high dimensional versions of code is kind of useful or even like necessary. But one difficulty in going to higher dimension is that well, it becomes more complicated. Like it's even just hard to just draw down this 3-dimensional or 4-dimensional pictures. And so what we need is sort of like a formalism that sort of nicely describe all of these objects. And that's exactly the main topic today, which is about this sheaf codes. So these sheaf codes are really like the higher dimensional version of the Tana code constructions. So today I won't give you like a very rigorous kind of definition. I invite you to like learn about it after the talk at home. For today, I'll just sort of illustrate the high-level ideas using examples from locally testable codes and quantum LDPC codes. And from there, you can build some intuitions on the cut product, which I'll also explain. Okay, but to get there, we'll have to first review some basic things. So we'll start by talking about quantum codes. Okay, so right. So okay, so what's a classical code? A classical code is about encoding k qubits into n qubits, k bits into n bits, and then these variables have to will satisfy some relations, so which are described by these parity checks. Okay, and these parity checks can then be used to detect and correct errors. Okay, so we know this very well. For quantum codes, it's actually kind of similar. So again, you have like these parity checks, so X check and Z check. But now there are two types of errors. So one is the usual 0 to 1 kind of bit flip error. But there is another kind, which is known as the phase flip error. So they would change the phase between 0 and 1. Okay, and because you have two types of error, so you sort of also have two types of checks. Okay. So far it's pretty similar to a classical code. But an important difference is that not all quantum measurements can be performed simultaneously. So what I mean is that to perform error correction, you have to measure syndrome. And the way you do that is to measure some of these X check and Z check. But it's not like any combination will work. Like only certain ones sort of make sense. So there's some extra relation or extra condition they have to satisfy. And the condition can be summarized into this, which is that for every pair of X and Z check, they have to share an even number of qubits. Okay, so for example, if you take these two checks, they share exactly on 2 qubits. Okay, so and you want to check this property for all pairs of X and Z's. There is a nice way to summarize this, which is to use the parity check matrix. So let's HX to be the parity check matrix that describes the X checks, and then HZ to be the one that describes the Z check. And turns out you can summarize the condition to just this simple formula, where the two matrices multiply into 0. So later on, I will refer to it as the orthogonality condition. And if you were there for the Pavel's lecture on chain complex, you would immediately recognize that, okay, the structure is identical to the condition for chain complex. And so, yeah, so that's why quantum codes and chain complex are very related. And yeah, so let me just give you a quick example. So one of the famous quantum code is known as the Tor code. So here I'm drawing a grid, and this grid is laid on a torus. So that means the top and the bottom are identified, and the left and the right are also identified. Okay, and then on this grid, there are some X check, qubits, and Z checks. And these segments indicates how the check act on the qubits. So the first thing we can do is to verify that, okay, this is indeed a quantum code. And so how do we verify it? Well, you need to make sure that for every pair of X and Z, they share an even number of qubits. Okay, so for example here, indeed they share an even number of qubits. So this, and you can check it for other pairs. They all satisfy it, and this really defines a quantum code. But importantly, this Tor code satisfies additional property known as this LDPC. So LDPC means that every check only acts on a constant number of qubits, and every qubit is only involved a constant number of checks. So for example, this check, it only acts on 4 qubits, and this qubits is only involved in these 4 checks. Okay. Yeah, so that means for Tor code, this number is really just 4. Yeah, so there are some practical reasons why like LDPC is an important property to have, but I won't go into that detail. What I'll say is just that these LDPC condition is also it's also basically saying that your parity matrix are like sparse matrices. Okay. So now I will move on and talk about these logical operators. So logical operators, they're really like the code words in classical codes. Yeah, so indeed, there are these X and Z logicals, CX and CZ, and they're exactly what you expect, um, which is yeah exactly the code that's induced from the Z and the X parity checks. But there is one important difference, which is that oh okay yeah so here is an example of the logical yeah essentially if you look at the vector which is 0 1 1 0 0 it satisfies all the Z checks. Okay, yeah, so far it just looks like a classical code. But important difference is that in quantum, some of these logical operators, they're in some sense like trivial. So trivial in the sense like, okay, like the all 0-bit strings is sort of trivial. And so what do I mean by that? So if you take an X check and look at the qubits that it acts on, turns out it's always a logical operator. And why is that? It's because of the orthogonality condition. Okay, so yeah. So what that means is that this image of HX is always part of the CX. It's always part of the logical operators. And for some physics reasons, these trivial ones, we actually really want to think of them as being just trivial. And so the actual logical operator in the quantum code is actually the quotient of the two. And for people familiar with chain complex, this is really like the homology or the cohomology of the chain complex. Okay, and let's look at the example again in this 2D Tor code. So let's see. So now we want to find some vectors acting on these qubits that satisfy the z-check. So that would gives us like a vector inside CX. Okay, and so here's one example. So and just to remember again, we are on a torus, so the left qubit is actually same as the right qubit. So really it's just two of these being ones. There are only two ones. And so you can check that, okay, for example, for this check, the sum of the four values is 0. Okay, and you can do that for other things. It's really, this example is one of the logical operators. Well, here's another example. You can, again, do the check. And if you just do more and more examples, you would begin to see that, okay, there seems to be a sense that these CX, they are like all possible loops on this torus. So for example, this green one is sort of like a loop going in the horizontal direction, and this cyan color is the one that goes in the sort of like the diagonal direction. Okay, what about the trivial logical operators? So recall the process is that you pick an X check and look at the qubit it acts on. So in this case, it'll be these 4 qubits. And the answer is that they correspond to these kind of contractible loops. Okay, yeah. So you can do some of these exercises at home, but we'll move on. So later on, what we'll do is that we will often draw this kind of cartoon picture to represent what is happening here. So one way to think about it is that if you make this torus, the grid finer and finer, these lines really becomes like a continuous line. And this is the kind of picture we'll be able to draw. And yeah, so this kind of cartoon picture, which is like continuous, like on a manifold, it's really like an important thing to have in mind, especially for one of the later discussions. Okay, but before moving on, let me just emphasize again, like this notion of trivial logical operators. So in classical codes, two words are the same if they're just the same. Okay, like their difference is 0. But in quantum, really, you only need their difference to be inside this trivial logical operators. So what that means is that these 3 pictures, they're really like the same thing because they're only differ by some contractible loops. And so importantly, what that means is that later on, when you see all these pictures, like you shouldn't think of it as, oops, you shouldn't think of it as just a line. Like it's not just a line. It's like a line, but you can deform it. Like like you have to think of like all these pictures in mind. They're really the same thing. Okay, so yeah, so it's about a homology class. Yeah. So yeah, this intuition will be useful later on. Okay. Now we have finished reviewing some quantum codes. Let's move on to the Tanner codes. So Tanner codes on a graph. So how do you construct a Tanner code on a graph? I'll go a bit faster here because I think many people have seen this before. So what you do is you first take a graph and you place the bits on the edges, and then you have some large check on the vertices. Okay, so what I mean is that your word would be some vector inside this f2 to the e, because each edge you can assign 0 or 1. And then when is such a vector a code word? It has to satisfy some conditions. So the condition is that you look at every vertex and you look at the adjacent values. So for example, this vertex is adjacent to these 3 edges. And you collect their values, and then you want to check that it's inside like a local code. Yeah, so in this case, the local code is 111. So that means these 3 values should be either 111 or 000. Okay, and so you want to check this for every vertex. Okay, and so just to summarize, the data that's used to construct this Tanner code is a graph and then some local codes on the vertices. Okay, so this is just a usual Tanner code. But here I want to describe a different perspective, a more geometric perspective. So what I want you to do is to think of each of these words as a one chain. So what's a one chain? This is just a collection of 1D objects. So in this case, there are these edges. And what we do is that for each word, we would pick the edges whose value is 1. Okay, so that would form like a collection of these edges, and that's our chain. And so now these local code conditions, they become this property that these edges has to end on the vertex in some specific way, specified by the local code. Okay, so for example, this vertex is saying that, okay, either the 3 edges are all present or all 3 of them are not present. Okay. So you might say, okay, why am I just telling you this story? Because it doesn't look so different from the classical case, from the previous case. But this actually will be very important once we talk about quantum code, which will come later. Okay, and that's the time to move on to the Sheaf codes. So as I said, I won't give you a very formal definition. I will just describe some examples. And we'll start with the example of locally testable codes. So I'll describe the construction in these 2 papers. So what you do is you first take a 2D square complex. So what's a 2D square complex? These are essentially like a bunch of these 2D squares, and then they're glued along the edges. Kind of similar to simplicial complex, except that now we are using squares. What you do next is you place the bits on the faces, and then there are some large checks along the edges. Okay, so again, the word that you consider would be inside f2 to the f, because for each face you can put 0 or 1. And now the edge would specify some condition on the adjacent faces. So for example, the adjacent value has to lie inside this code space, like this local code. Okay, yeah, so this is kind of straightforward. The data now becomes like a 2D complex and some local code conditions along the edges. Okay, and now again, I want you to think about the geometric kind of perspective. So now I want you to think of each word as a 2 chain. Okay, and 2 chain is just a collection of 2D objects, in this case, the faces. And the mapping is again straightforward. If the value is 1, then you take the face, otherwise you don't take the face. Okay. And again, these faces would have to end on the edges in some very special ways. That's determined by these local codes. Okay, so yeah, so this is the case for this locally testable codes. Later on, we'll move on to quantum, but that becomes more challenging. So now I'll just pause a little bit and uh, let's just like imagine again like what's going on now. So you can close our eyes if you want to. So what we have in mind now is that we have some underlying square complex. So just a bunch of squares glued on the edges. And on top of this base kind of complex, what are the code words? The code words are a collection of these faces, such that they end on the edges in some specific way. Okay, so this is the current situation, and later on we'll do a same kind of exercise for the quantum case, and we'll see it now. So for the quantum code, as I mentioned, there is this construction by Panteleev and Kalachev, but later on there are also two other constructions, like variants of it. So in all these three constructions, the first step is, again, still the same. Just take a 2D square complex. But then the next step becomes very different. So in Panteleev and Kalachev, what their papers say is that now you play the qubits on the faces and the vertices, and then you put the x and z check in some horizontal and vertical edges. Well, for Zemmour, it says something completely different. It says you place the qubits on the faces, and then the checks and the checks on the vertices, and you don't use the edges. Okay, somehow. But in the last case, it's again different. So you put the qubits on the edges, x checks on the vertices, and z checks on the faces. So you can see they're just completely different. And why are there so many different descriptions? Is there sort of a unifying story here? Well, it turns out the answer is yes, and that's what I'm trying to explain next. And this would rely on the geometric picture that we were describing. Okay, so let's begin. So again, you take the square complex. Next thing you do is want to use the geometric picture. So now the words are the one chains. So what I mean is that you have this base graph, a base complex, two-dimensional, and on top of it, there are a bunch of these like one chain on it, kind of like a spaghetti, like a bunch of lines. And these paths, yeah, I'll refer to these lines as paths because now they can curve around in arbitrary ways. So these paths, they have to end on these boundary, like these edges, in a, again, specific way determined by the local code. Okay? So for example, if your local code is 111, then these three lines, they're either all present or none of them are present. Okay? And so again, the data is same as before. It's again a 2D complex with some local code that are defined on the edges. Okay, and so let's now just imagine the situation again. The situation now is that you have the sphere complex, and on top of it, there are these spaghetti, like just a bunch of lines, and these lines are moving around. As I said, because everything are only defined up to trivial, like logical operators, so these lines can really like wiggle around. And then for code words, these lines had to end on the boundary in these ways defined by the local codes. Okay. So what I'll say is that this picture turns out to be very satisfying because that sort of unifies these three different perspectives. So in particular, all these three codes can have like a spaghetti picture. So let me just give you some example. So for this code by Olivier Zamor, the qubits are at the faces, right? So how do you turn that into a spaghetti picture? Well, if the face has value 1, then you draw the diagonal line. And otherwise you don't. Okay, so that converts into this kind of picture with a bunch of lines. What about this code? Here, so now these qubits are on the edges. And so what happens is that these qubits would determine the structure near that edge. So for example, the value for this edge would tell you like how this branching work out, like just along that edge. Okay, And then the red check would just say that, oh, like there has to be even number of things coming in. And yeah, these are, yeah. Oh, anyway, like the point is that now you can turn that into this kind of spaghetti picture, and you can do the same for the Panteleev and Kalachev case. Okay. And currently it looks like these pictures are all very different. But as I mentioned, um, in quantum codes, things are only defined up to like trivial logical operators. So you can actually move these spaghetti around to make them the same. Okay. I won't demonstrate it, but yeah, indeed, they're all the same. Okay, and now let's leads to the like a version, a definition for sheaf codes. So again, this is very informal with a bunch of asterisks. Okay, so what we do is to take a t-dimensional cell complex with some local code that is defined on the codimension one boundary, codimension one cells. So that's t minus one cells. Okay, and how do you construct this the vector spaces for your chain complex? These would be all the I chains that satisfy the boundary conditions. So boundary condition is what I mean by these local code conditions. So for example, the one of the thing we discussed is in C2, we would denote as C2, and then this quantum code case would denote it as C1. And now that you can use them to construct your chain complex. So CT to CT minus 1 all the way to C0. And there are some natural boundary operations that defines these map, but I won't go into the detail today. But as I say, there are a bunch of asterisks, so let me say a few words. So one of them is that it's not the case that you just take any local codes. There are actually some like crazy conditions on them. Roughly speaking, it's like some exact sequence conditions, or like also known as these acyclic conditions. So you can find them more in the paper. Another thing is that this chain complex, the chain that we were describing today, they they sort of just cover all the faces, right? Like we just take the face or we don't take the face. But actually, in these definitions, you're allowed to take like part of the face. Like for example, there's a hole that you don't take inside this space, things like that. And so there's something that's I didn't describe all the detail, but that's sort of the big picture. And the point is that with these kind of
David, about
def
5 minutes.
yeah, okay, yeah. So with these right, so with these language of sheaf codes, it actually comes with some nice properties. So one of them is these Poincare duality. Um, okay, I won't explain too much detail, but um, in the proof of distance, there's often the distance for the x check and the z check. The distance, like the x distance and the z distance. And turns out using this Poincare duality, you can often reduce the proof of x distance into just the z distance. Okay, so anyway, that's one of the kind of useful thing, like an important toolkit in the proof for quantum locally testable code for that paper. And as I say, another thing that we will focus on today is this cup product, which allows you to access these kind of multiplication kind of property. Okay, so cup product. So that's the last thing we'll talk about today. So before going to the quantum case, let me just quickly remind you what's the kind of situation for the classical code. So for classical code, C and C prime and C double prime, we'll say that they have a multiplication property if C or dot C prime is inside C double prime. So what I mean by this dot is an entry-wise product. So in C and C prime would have the same length, and you can just multiply their entries directly. Okay, and as a code, you would take a span of all the possible dots between C and C prime. Okay, so as I mentioned, like when you take an end, like a logical end, it's very related to multiplication. Yeah, so that's why we want to discuss these kind of properties, and some of them are actually useful for constructing PCPs. So But on the other hand, this kind of property is actually kind of non-trivial because in many cases, if you just take arbitrary CNC prime, actually their dot is actually just a full vector space. Okay, so when can you have a non-trivial property? It's kind of a tricky question. Okay, actually, in many cases, they come from some algebraic properties, such as like Reed-Solomon code. They will have this kind of features. Um, okay, but back to our context. What we want to discuss today is the Tanner code. And so Tanner code is a very useful tool in the sense that you can like turn small local codes into some large codes. And actually, this feature also carries for these multiplication properties. So you have two Tanner codes that are built from these local codes CV and CV prime. Their dot, like these dot of these large codes, it actually becomes a Tanner code with local code CV dot CV prime. So what that means is that if your local code have some multiplication property, actually your global, like this Tanner code, also have some sort of nice multiplication properties. Okay, and what I want to say is essentially that this property is also, you also have a similar feature for these quantum codes. So let me just quickly, briefly explain this. So now your complex is no longer two-dimensional, it's three-dimensional. So in this three-dimensional complex, you have these logical operators. These logical operators become these surfaces. So for example, this blue surface over here, and then this green surface over here. And so again, these surfaces have to end on the top face in a certain way, determined by these codes, CF and CF prime. So what we'll do next is to really just take their intersection. So if you take two planes on a 3D, they will intersect at some lines. And so what you get is a bunch of paths, like a bunch of paths, and so that forms a one chain. And you can ask, okay, what's the pattern near this top face? Well, the answer is that it's C dot C prime. And the reason is just that, okay, when do you have an edge? It's when both of these planes are present. And so that's exactly this C dot C prime feature. Okay. And so what I'll say at the end is that it's really this feature that I'm describing here that gives you the cup product for these sheaf codes. Okay, so I'll just conclude there. So today we sort of described two things. One is this kind of geometric perspective for sheaf codes, and that allows you to sort of understand these logical operator very like geometrically. And from there, we can use them to induce these intersection that leads to these cup products. Yeah, so at the end, there are still a bunch of open questions. But today, I just give you sort of the kind of overall pictures. So we won't describe the detail of like what these open question means. But I'll just say that currently, um, the parameters aren't optimal yet, and so there is still room for improvement, and that's kind of an interesting direction here. Yeah. Okay. So that's all.
Take a question or two while the next speaker maybe sets up. Yeah. I can repeat the question maybe. Yeah. Yeah. So David, the second question was, is the second theorem using the three-dimensional complex in the last slide?
Second theorem. Yes. This one is using the three-dimensional complex, and this top one is using the four-dimensional complex.
Maybe I have a quick question on this intersection thing you mentioned. Do you have to be careful on how you make those faces intersect in terms of that geometry?
Um, I see. Do you mean that here I
Yeah,
just I
yeah,
sort
the
of just
blue.
simply draw the blue in this direction and green the other direction? Like what happens if they're just curved in some other ways? Is that
Or yeah, I guess does some geometry guide that choice of how the faces
oh,
are?
geometry? Um, I would say not really. So okay. So maybe okay, what I have in mind is that um, even though most of the current construction is using these kind of cubical complex, but really it's necessary property. Like one can take some simplicial complex, for example, like all these high-dimensional expander, you can actually also put local codes on them. Like the Sheaf code language also applies in those contexts too.
I see. Okay. No further question. Thanks a lot, David, for the great talk.
Yeah, thanks.
Yeah, I guess we are right on time.